Hi everyone, thanks for being here. Today I'm going to present our work, Steering Prototypes with Prompt Tuning for Rehearsal-Free Continual Learning. So first of all, I'm going to give a very simple introduction to the continual learning topic. So let's start by compare continual learning to single task learning and multitask learning. So for single task learning, we are training and testing on the same task, and the model is expected to perform well on the targeted task. For multitask learning, we simultaneously train the model on multiple tasks and hope the model can be excel at all the given tasks. So similar to the multitask learning, continual learning also aims to enable a single model to be good at several tasks simultaneously. However, instead of learning on those tasks concurrently, continual learning learns them sequentially. That means at each time step, the model is only accessible to the current task and its corresponding data. Yet we want the learned models to be good at all previous learned tasks. So continual learning is actually a very natural capabilities for human beings. For example, we won't forget how to swim after we learn how to drive a car. However, this seemingly natural ability does not easily transfer to our neural networks. Naive continual learning for the neural networks ends up to having catastrophic forgetting issue. That means the neural networks catastrophically forget the previous learned tasks while learning on the new task. To mitigate catastrophic forgetting issue, there are a large amount of methods that has been proposed, and they can be coarsely categorized into three groups. So the first group is a memory-based method. They selectively save some data instances from previous learned tasks and rehearse on them while learning new tasks. This kind of method is simple and generate decent performance. However, it needs to save explicitly some amount of data in memory and do extra rehearsal on them. And another line of research uses a regularization term to prevent weights from altering too much from previous tasks. They don't need to save any training on memory examples, but not surprisingly, their performance downgrades as task sequence goes along. And finally, there are some other works advocate for separate subnetworks for different tasks. They show good performance, but they are memory demanding and hard to scale up. So in this work, we are trying to propose a new strategy to both prevent catastrophic forgetting and also remain memory and computational efficient at the same time. Now let's go back to the origin of the catastrophic forgetting. So the generation of catastrophic forgetting can be attributed to the weight sharing scheme for the connectionist model. Let's say if there is an axis representing the extent of the weight sharing, then on the one end, we can train a separate network for each task. Then there will be no weight sharing and no forgetting. And this naive scheme will need to keep, n duplicates of the different models. And on the other end of this axis, we can fully share all the parameters and use a rehearsal-based method or other regularization terms to reduce the forgetting. So we wonder if there's something in between and can we do better? And also from now on, we will only consider the image classification tasks. In order to enjoy both the knowledge sharing due to the weight sharing and avoiding forgetting due to the parameter isolation, we propose our first module, task-specific prompt tuning. We still gonna share majority of the weights, yet we keep them frozen. This part corresponds to a pre-trained transformer in our framework. Then we optimize the task-specific prompt during the learning of each task, and then we prompt the frozen model to become an expert model for the target task. And at the inference, given a frozen backbone, if we can correctly retrieve match the prompt for the targeted task we want to solve, then we will be able to solve it better. Now the question turns to how to retrieve the correct task-specific prompt during the inference. Here we are dealing with a challenging scenario where we don't assume that we know the task ID of our given data, so we need to infer the task ID at test time. To retrieve the correct task ID for data actually involves two sub-questions. First, what is the task ID? How do we define it? Then the question is how to retrieve it given a data sample at test time. Above two questions actually motivated the design of the following two modules. First, our framework is a prototype-centered framework. We generate K prototypes for each class using the frozen transformer, and they serve as the keys for retrieving task IDs. We also generate value prototypes, use both the frozen part and the learned task-specific prompts, and those value prototypes function as the final classifiers. At inference, we perform a cost-to-find retrieval process. This process involves first to generate a query from the data using the frozen transformer. Then we compare the query with all the key prototypes and use KN method to keep the several nearest K prototypes as candidate task IDs. Then we use the task-specific prompt associated with those candidate task IDs to generate fine-grained queries, and measure the pairwise similarity between those fine-grained queries and value prototypes to perform the final classification. So with this prototype-centered framework augmented with a retrieval system, we can readily perform continual learning with minimum forgetting. But there is still something left behind. That is how to optimize those task-specific prompts and how to guarantee that a prototype is representative for a given class. To address concerns from last slide, we propose a prototypical contrast loss to optimize the prompts. This loss operates by aggregating intra-class samples while diverging inter-class samples, so that there should be less interference between prototypes from different classes. Since we are only accessible to data of current tasks, we always save prototypes from previous learned tasks and set them as negative anchors in the latent space to avoid overlapping between the prototypes of new tasks and old tasks. Beyond the contrastive prototypical loss, we further devise a multi-centroid prototype strategy to enhance the prototype. So instead of using the class min center as a prototype, we actually generate a multi-centroid for a class using the spectral clustering method and make the prototype more powerful for non-isotropic distribution. Here, in this slide, we're going to show some empirical results. We first benchmark the performance of our method on several well-known and challenging datasets. As can be seen that our method outperforms existing methods by a very large margin. Since our method relies on a pre-trained transformer and we design several different modules, it is critical to see how those proposed modules act against the different pre-training methods. And by collecting a wide range of representative pre-training methods, we can see in table that or each proposed modules are effective under different pre-training methods, and their benefits are additive. Beyond strong performance, memory efficiency is also another merit, and as can be shown from the table 5, our method is very memory efficient. Finally, we show some visualization results. In this slide, the left figure plots data points without using our method, and the right part denotes the opposite. And as expected, our method effectively separates different classes during the continual learning setup. Finally, we're going to end this talk with a conclusion. And in this slide, I'm going to summarize the advantages of our method and also point out some limitations. So, our method, by devising task-specific prompt and use cost-to-find retrieval mechanism, our method actually achieves minimum forgetting. And by combining task-specific prompt with prototypes, we also avoid doing rehearsal, which means it is more computationally efficient during the training. And since for each incremental task, we only need to save a few low-dimensional prototypes and a prompt. That means it is also memory efficient. And also, due to the use of synthetic prototypes than the real data, it also respects the privacy. Despite all those merits, we also have some limitations. Due to the design of cost-to-find retrieval process, we may actually need more than one forward pass at inference. And also, this framework is primarily designed for the classification task, which means it needs to perform further adaptation for other tasks. And thanks for listening.